So good afternoon, sir. My name is Aman and my friend Prakhar. We are going to show you the simulation of analysis of heat distribution in compressor film. For the simulation, we are using a finite element analysis software called ANSYS. In this toolbox, we are using the steady state thermal. So first, we drag and drop this steady state thermal to the projected schematics. And in that, we'll first go for the engineering data. Uh, by default, it is a structural STD saved. We change the material as aluminum alloy. Now we'll go for the isotropic thermal conductivity. We save its unit as watt per meter Kelvin. This aluminum alloy has the thermal conductivity of 276 watt per meter Kelvin. Here we can see the graph also temperature versus thermal conductivity. So the material is added. Now we close this engineering data tab and we'll import this geometry. We'll design the geometry using the SolidWorks, and in browse we'll open the compressor film. I name as .stp and open this. Now we can show the geometry has also geometry has been uploaded. Then go for the model by double click. Here you can see the starting mechanical. It will take some time to open this tab. Hmm. The model is ready. Now we'll go for the meshing. First we'll do the by default mesh. Click on generate mesh. Now the mesh is ready, but the quality of mesh is not fine. So to get a better accuracy in the result, we'll decrease the mesh size. And this meshing is nothing but discretization of model into different number of pieces. And for that, we go for the mesh sizing, and we'll select all the model by pressing the Control A button. Now the model has been selected. And say apply. Here you can see the element size is 5.2 mm. We'll decrease the element size as to 2 mm and press OK. Now again, we go for the update mesh, or you can say generate mesh. Now you can see the mesh quality is better. Uh, from this statics, we can also see the total number of nodes and elements. In our case, it is 71,748 nodes and 39,019 elements. Now the meshing is done. This is the fourth step of the problem. Now we'll go for the steady state thermal. In that, go to the insert, and in that we'll go for the temperature. We'll select the in which phase we have to apply the temperature. So we are applying the temperature on this phase as well as this phase, and the inner surface also. Now say apply. In the red color, we can see the temperature is applied on this phase, inner as well as outer. Now we have given the boundary condition. Now we'll go for the solution. In solution, we have to find the uh, uh, temperature other than total heat flux, and after that directional heat flux. And after that, we'll show the solve the solution part. This is the sixth step of the problem. In basically in FEA software, we can solve any problem in seven steps. First one is the material selection. Second one is either we can import the model using the other software, or we can design this model into the design modular tab. And third one is the meshing, and fourth one is boundary condition. Fifth one is solution, and the sixth one is we'll analyze the result, or we can say it's a animation part. So now here we can see the solution has been ready. It is the temperature, total heat flux, and directional heat flux. Same temperature, we can see the maximum and minimum both the temperature is same. Sorry, we haven't given the temperature at this stage, so we are giving the 600 degree Celsius as temperature. Now we'll again go for the solve. Solution is ready now. So the maximum minimum temperature at all the surfaces is all the faces is same, which is 600 degrees Celsius. We have given the time as for 1 second. We can see its animation part also by increasing the time step at 4 seconds. This is the temperature. Now we'll go for the total heat flux. The total heat flux is maximum at this phases. This still shows the result of the data. Like at different and different points, this total heat flux is different. This here the red color shows the heat flux is maximum at this interface, and this blue color shows the minimum of all the fill part, that is rounded circle. We can also show its animation. See how total heat flux gets distributed, and it is maximum at this corner of the table circle. Now the total heat flux is ready. Now we'll go for the directional heat flux. You can also see the result, like this maximum at maximum value is 1.4 into E into 10 to the power minus 11. It's the maximum value. You can see at this point interface, which is shown in the red color, and the minimum is minus 1.045 into e raised to the power minus 11. That is in blue color, which is shown at this interface. We can show its animation also. I will get animated. Here you can show the red and blue color. After that, I stop the animation. So we have almost completed all the parts. Like we have first imported the geometry using SolidWorks. After that, we'll select the material as aluminum alloy. Then after we did the meshing of the element size of 2 mm. There you can see the face size of 2 mm. And we have given the boundary condition as temperature. As temperature, we have applied to this face, that's shown in the red color. And the temperature is 1600 degrees Celsius. After that, we'll go for the solution, that is temperature, total heat flux, as well as directional heat flux.
So, my name is Prafar Patwardhan and my teammate name is Aman Kumar. And our topic is analysis of heat distribution in compressor fin. So, coming to the introduction part, overview of compressor fin. Compressor fins are crucial components in various machinery, particularly in engines and HVAC systems. They function to dissipate excess heat generated during compression, ensuring the compressor operates efficiently and reliably. Effective heat management in compressor fins vital to prevent overheating, which can lead to component failure and reduce system efficiency. So our objective is the primary goal of this study is to analyze the heat distribution across the compressor fin using ANSYS software. So by understanding thermal behavior, we can identify areas where heat dissipation is optimized or where improvements are needed. For the fin geometry modeling, the fin geometry was created using ANSYS design modeler or imported from CAD software. The second point is of methodology is material selection. We are taking aluminum material, and here are the thermal properties. So the third point is meshing. The fourth point is boundary condition. Now coming to heat distribution analysis. Temperature distribution. The temperature distribution across the fin was obtained from the ANSYS simulation. Second point is heat flux. So the visual representation, arrow indicates the flow of heat from the base towards the tip of the fin, with longer arrows representing higher flux. Discussion. The first point of discussion is efficiency of the fin design in dissipating heat. Second point is localized hotspots. The third point is impact of material properties. So now coming to comparison with theoretical data. The first point is alignment with theoretical expectations. Second point is discrepancies. Now the potential area of optimization come to geometric adjustment. Modifying the fin's geometry such as tapering or adding additional surface feature could improve heat dissipation and reduce hotspots. Second point is material consideration. So the first point is investigating alternative materials with higher thermal conductivity or better heat resistance could further improve the fin effectiveness. So the conclusion of this entire presentation is so the first point is effective dissipation. The compressor fin effectively dissipate heat with a clear temperature gradient from the base to the tip. Localized hotspots. The hotspots were identified indicating areas for potential design improvement to reduce thermal stress. The role of ANSYS. ANSYS enabled accurate simulation of heat distribution, validating the fin design and identifying areas for optimization. Future work. Focus on design adjustment to eliminate hotspots and explore alternative material to enhance thermal performance. Thank you.